Parameterization 15F. This is the second part of this exercise. So today we're going to work backwards. So we know to convert from parametric to Cartesian, we need to eliminate the parameter t. But how do we convert from Cartesian to parametric? So that means how do we convert if we have y equals some function of x to two separate equations, x equals a function of time and y also equals a different function of time. So I've got to write x in terms of t and y in terms of t. We do this using substitution, and it depends on the type of equation. For instance, if our Cartesian equation is a line, we're going to try something simple like substituting x equals t and see what happens. So let's try the simple things like a line. Example 1, we have the Cartesian equation y equals 2x minus 1. We need to find x as a function of time and y as a different function of time. So I'm just going to say, let's let x equals t. Then y would be, well, wherever you see an x, put a t in the Cartesian equation, we'll get y equals 2t minus 1. So very quickly, I've found my Cartesian equation and I've changed it into two parametric equations. Now, if you sub 1 into 2, you should get your Cartesian or original back. So if we have y equals 2t minus 1, I know that I let x equals t. So everywhere I see t, I put an x, and I end up back with y equals 2x minus 1. That's good. The next one, we have a few options, but we're going to try the same thing. So to get our two parametric equations, let's just let x equals t. That's my equation for x. So then y would be, well, everywhere I see an x in my Cartesian, I just put a t. I'll get y equals t squared over 9 minus t over 3. And these are our two parametric equations. Of course, there's a few solutions and a few ways you can do this. There's not just one unique answer. So, for instance, a different method could be to let x equal something different. I can see both of these terms in my Cartesian equation have an x over 3. So I could potentially let x over 3 equal t. I always need to write my parametric equation in terms of x, so I'll get x equals 3t just by multiplying by 3. Then for my y equation, well, wherever I see an x in my Cartesian, I'm just going to put 3t. So I'll get y equals 3t all squared on 9 minus 3t on 3. This is nice, it will cancel, and I'll get a very simple equation. The 9's will cancel, I'll just be left with t squared. The 3's will cancel, I'll just have t. So I have y equals t squared minus t, and x equals 3t. Those two are my parametric equations. Again, you can check this result by putting x over 3 into your y equation, and hopefully you get back your original Cartesian, which we do. Last two examples. So the first one, remember this looks like a circle. So from my table of hints, I need to use the fact that cos squared t plus sine squared t equals 1. And I'll show you why. So let's have a look. Again, we need x equals a function of t and y equals a function of t. So I have x equals f of t and y equals g of t. So I want my circle to look something like something squared plus something squared equals 1. To do that, I'm going to divide both sides of my Cartesian equation by 4. So I'll get x plus 1 squared all over 4 plus y plus 3 squared over 4 equals 4 divided by 4 is 1. Now, because I want something squared plus something squared, I'm going to rearrange this, and I could have x plus 1 all over 2 squared, right? That's the same thing as the above line, plus y plus 3 all over 2 squared equals 1. This is where I use the fact that cos squared t plus sine squared t equals 1. And then I can simply kind of match up the terms here with cos squared and sine squared because the equations look pretty similar. So let's let x plus 1 over 2 squared, that will be my cos squared, and y plus 3 over 2 all squared will be my sine squared. What does this mean? This means that then cos t would be x plus 1 all over 2, and my sine t would be y plus 3 over 2. We're going to rewrite then two separate equations, which is what I want, one involving x, one involving y, and they both involve t. I'm going to rearrange to create x as my subject, so I'd have x plus 1 over 2 equals cos t, then times by 2 and minus the 1, I'll get x equals 2 cos t minus 1. For y is similar. I start off with y plus 3 over 2 is sine t, times by 2 minus 3, and I end up with y equals 2 sine t minus 3. Lastly, I have x plus 2 all squared over 4 minus y minus 3 all squared over 16 equals 1. Now this isn't a circle, it's not an ellipse, it's actually a hyperbola. So notice the minus sign. The Pythagorean identity I know with a minus sign is sec squared t minus tan squared t equals 1. So that's what we're going to use for this one. Firstly, I need something squared minus something squared equals 1. So I just will take the 4 and make it 2 squared. So x plus 2 all over 2 squared minus, again, 16, the square root is 4. So I could have y minus 3 over 4 all squared equals 1. We know that sec squared t minus tan squared t equals 1. So I'm just going to let, again, kind of equating these equations and the parts of the equations. We let x plus 2 all over 2 equals sec t, and y minus 3 all over 4 equals tan t, then rearrange for x and y. My two parametric equations become x equals 2 sec t minus 2 and y equals 4 tan t plus 3.